welcome to another lecture on linear programming. We are looking at Yau's Minimax theorem. We are going to look at the proof once again in a slightly different light. Hopefully this clarifies things. Remember, what do we want to do? We had defined the model of communication complexity. We said in the case of randomized communication complexity, if we fix a function f, then the average case complexity over distribution mu, the maximum average case complexity over mu is equal to the worst case complexity, right? The reason why we want to view it like this is actually here the model of communication complexity, the way we define the complexity are not that important. In most of the randomized settings, this kind of a theorem works, and I want to give you an intuition of why, right? So if you look at this statement, max over mu, average case complexity mu, worst case equal to worst case complexity, I am not defining what I mean by average case complexity. I am not defining by what I mean by worst case complexity in that particular model. But in general, what is a worst case complexity, right? For an algorithm, we define the worst case complexity to be maximum over x comma y, cost of the algorithm, right? So maximum over input x, this is the cost of a, cost of any algorithm, or it could be a protocol, whatever you want to think of, correct? And then now my worst case complexity is going to be min over all possible algorithms or protocols, because obviously I want to choose the best algorithm or a protocol. And again, remember which model is this, how exactly I define the cost, I am not talking about it, right? Similarly, if I talk about this quantity on the LHS, right? What is the average case complexity over mu? This is minimize over all algorithms, correct? Or I should say not complexity, but cost of A. Correct? Now, cost of A does not depend on x, because there is a distribution I have in mind, right? So that's why I can't write it as A of x. It is summation mu x ax, right? And then if I want to maximize over mu, this looks like max over mu min over A cost of A, right? So you already see min max kind of coming into the play, right? And this is true for lot of randomized situations, query complexity, communication complexity, Las Vegas, Monte Carlo. For almost all of them, you can still show this kind of a result. And again, the intuition is this, that all of them look like maximum. They already form a min-max structure. The point is, in that model, can you construct a nice value of cost so that these things make sense? Sounds good? What is the average case complexity of mu? What do I mean by that? I assume that my input distribution is from mu. My x is coming out from mu, and then what is the cost? So that would be, so my x comes with this probability, and then cost of x, right? This is why this is worst case, max over x. This is average case, right? Average case means according to a probability distribution. If this input distribution was uniform, this would be the average cost. So average cost is just generalizing this term where my weight on my x could be different. Okay, so that's why this is an average cost with respect to the distribution.
The max means this.
Sorry?
The maximizing.
No, this means, this cost means this. So once I fix the distribution in mind, the cost with respect to that distribution of an algorithm is this. And then if I want to figure out the worst case complexity, I am saying you take the maximum over all possible distributions, the average case complexity turns out to be worst case complexity. Okay? So this max mu is not part of cost. I am saying if you maximize the cost, average cost, over all possible distributions, it turns out to be worst case. That's the importance of this statement. Right? So now we want to set up this thing for our communication complexity model, right? And again, if I want to prove this thing, one thing is average case cost of mu is less than worst case cost. This is okay, right? This is the easy part. This is in some sense the weak duality, right? Because this is saying that if I work, if in C cost I can answer on every input, that means in C cost I can answer on any distribution of inputs also. That's not surprising, right? So then my worst case has to be bigger than this. And now the important question is how to prove the equality, right? So to prove this, then we take the LHS to be C. Notice when I call it cost, but it could be any measure of the algorithm. Like yesterday it was the success probability, right? So don't get confused by cost word. It need not be the communication cost. It need not be the communication bits exchange. It is sub measure of how hard it is for an algorithm to perform, right? So you can say that, oh, fix an error, how much communication am I taking? That's a measure of cost. Other way to view the same thing is, you say, oh, you are only allowed C communication. How much error can you make, right? So we are viewing it in the opposite way for this kind of setting. Okay. So max average cost mu, this is what you want to analyze. I am calling this C. Okay, I want to show that there is a worst case algorithm which works with C cost. Okay. What does it mean? For any mu, there exists a protocol, a randomized protocol, probably a protocol P, which succeeds with probability greater than. So this is, in other words, for all. This is the statement I am making about C. Sounds good? This is how I am defining C. It's this quantity, in other words, in this much communication, in this much communication, for any mu, I have a randomized protocol which is going to work. This is the definition of working, right? Now, after setting this, now I am going to do a max-min, but this average cost is going to be completely different. It is not going to talk about communication. Okay? So, I am going to set these things up, define A. What do I want? I want inputs here, protocols, and again when I say protocols, they have communication cost less than equal to C. Okay? So now after defining this, I am going to now view of it is I have C amount of communication, I have fixed that amount of communication. How much error do I have to make? Right? So this is a setting up, and then just to have a change, now let's say define this to be the indicator that protocol fails on the input. Right? If I look at this entry, this corresponds to an input and a protocol. So I am defining it to be 1 if it fails, I am defining it to be 0 if it succeeds. Right?
So that symbol means, I mean, like
Indicator. Generally, when someone writes like this is 1 and then some binary condition. So it says that if this condition is true, then you take the value 1, otherwise 0. Okay? This is the notation. Great. Clear how I have defined the matrix A? Now, for any input distribution, and a randomized algorithm. Remember, a randomized algorithm is a distribution over these protocols. Correct? What is the meaning of this? This is summation over all protocols in P, whatever is the support of P, summation over all input pairs. Correct? I pick the input pair, I pick the deterministic protocol, and then ask P1 fails on X comma Y or not. Right? Now, for a randomized protocol, what is the probability of failing? Pick up these things with their original probability and then say what is the failure probability. Right? If you have a protocol which fails with probability 1 by 3, if you have a protocol which fails with probability half, and you are taking a equal mixture of those, what is your failure probability? Half times 1 by 3 plus half times half. Right? So this is basically failure probability of capital P. P when input is coming from okay. Notice this P is this mu xy. Okay. So let me just write it one more time. This is summation over protocol. These are the protocols, deterministic protocols, which I will be utilizing in my randomized protocol. P fails X comma y. Right? So what is this? Failure probability of, what is this quantity? The failure of probability Pi on mu. Right? And if I am taking Pi with this much probability, then this is the failure probability over the randomized protocol. Correct? So this is how you can parse this statement. Right? So, and if still not clear, after the class I can explain it again. This is the failure probability. Now, knowing this, let's write down the average case complexity, or average case. What do we want to do? We want to minimize over all possible mu sorry, I want to maximize over mu, or forget it, think about this, minimize over all possible. If I fix mu, I want to minimize the error probability. Right? What did the definition of C tell me? I know for any mu, there always exists a protocol which succeeds with probability 2 by 3. That means fails with probability at most 1 by 3. That means if I fix a mu, there exists a protocol such that this error is less than 1 by 3. If this error is less than 1 by 3 for any mu, right? So for all mu, this quantity, let's say error with respect to mu, less than. This implies this is less than. Good. Today I am lucky. I have used the definition of C and now I can erase it. Right? So now this is less than 1 by 3. This is a max-min. Now I am ready to use my von Neumann's maximin or min-max theorem. So I know now that min over P max over mu less than 1 by 3. Right? This is just directly coming from duality, strong duality or von Neumann's min-max. Now once I know this, what does this tell me? Suppose optimal here is attained by P0. This is the optimal solution for above. Right? What is P0? It's a randomized protocol. It's a distribution over deterministic protocols with cost at most C. That means it's a randomized protocol with communication cost C. Right? So P0 with communication right. What do I know about this? For this particular P, right, a simple consequence of this is max over xy probability P errs on xy after this here, right? So max mu transpose AP. I am saying if this is the case, let's look at all the point distributions. Fix mu to be a particular input x comma y. Then this is kind of a one vector, right? Standard basis vector. And then what I get here is probability that P errs on that particular input x comma y. In this, there is only one mu xy which is 1, everything else is 0. Right? So then this is the probability that P makes an error or fails on x comma y. So now this is saying that I have a communication I have a protocol whose communication cost is less than C and it works for every input. Communication C works on every input, every distribution of input, one and the same thing, right? This implies now in the worst case, communication cost This is what I wanted to show. Right? So I guess the one problem in this is that I start with a cost where the cost was in terms of communication cost, how much I was doing, right? And then we define the cost as, oh, if the error is 2 by 3, how much communication do I need? But when I want to prove this theorem, the way I have set up my matrix A, yes, it turns out to be asking the question in the equivalent but opposite way. I say that let's fix my communication and say how less an error can I make, right? And then everything works out. Make sense? The punchline again is here that the way I have defined the cost is not very important. There are multiple models, there are multiple ways in which you can set up the same experiment and you can get the similar theorem. Okay? So Yao's min-max is not just one theorem. For many randomized models, for many settings, you can always say that the worst case complexity is equal to the maximum average case complexity. Okay. And now, once again, why is it so great? It's actually telling you something very fundamental, which is great. So let me just write it in the what was it? Min over, we will exchange if required. Sorry, I have to reverse it, right? I always get it the wrong way. Right? This is the max average cost. I reverse it, think of it again, look at worst possible input, take the best algorithm, right? So this, the way to remember is, if I am taking the cost, I want to minimize over the protocols. If I am taking the success probability here, then I want to maximize over all possible protocols. So yesterday we had the opposite order of min-max, because here it was success probability and not the cost. Okay, and the main reason why this theorem is so fantastic is because it allows us to put lower bound on worst case. Like we have, yes, question? Max of, sorry. I shouldn't say worst case. You are right. Ideally, I shouldn't say case. I should say cost of, in some sense, p comma mu, and here I will say cost of p comma mu. It will actually be the same thing, which is, yes, you are right. You are right. Right. So I would say cost of p comma mu, and this I have not defined. So now, like in the case of other duality examples, remember what happens is, we want to put a lower bound on worst case, duality changes it into a max problem. That means if I can at any point for any mu min over p, cost p mu is a lower bound on worst case complexity, right? This is trivial. It's a maximization problem. If I take a feasible solution, I will get a lower bound, right? More importantly, since I am now only worried about this, do I have to worry about taking a randomized protocol? No, the minimum will be attained at a vertex. So then I can say min over deterministic protocols. Okay. So, to show that some problem is really hard, I just want to construct a nice mu such that every deterministic protocol, not randomized protocol, remember I wanted to give a lower bound on randomized protocols, which is a much harder thing, much bigger set. But because of this min-max theorem, I have changed it to saying find a nice distribution so that even just the deterministic protocols don't work. Okay.